Let's just briefly look at some other notation in your text that deals with what your text likes to call index collections of sets. What this is doing is it's using the union and intersection symbols that we've just been doing, kind of like the way we were using the summation and the pi symbols before, where we're going through a collection of sets that are in a sequence. So we can have a group of sets, and we can talk about doing the union of all of those sets. If the sets go from a sub 0 to a sub n, we can do the union going from 0 to n of these. And if we have infinite number of sets, that's what the little kind of an 8 symbol sitting on the side means, an infinite number of sets, we can actually do unions of things going out to infinity, which happens when we work with sets that have no ends, like the set of all integers or the set of all rational numbers. We can do unions in much the same way. And they do a few problems looking at things this way. There's a number of other vocabulary terms that we need to look at that will eventually help us with the definition of something called a partition. First of all, we're going to say that two sets are disjoint if and only if they have no elements in common. So we're saying A and B are disjoint if and only if their intersection is the null set. What we're doing there is we are drawing that A intersection B is equal to the null set, is saying these two sets are disjoint. When we extend the idea of being disjoint to multiple sets, where you have a group of sets in a collection, like we just showed with a union or an intersection, we can say that all of the sets in this collection are either mutually disjoint or pairwise disjoint or non-overlapping. All those words mean the same thing. If you take any two of the sets, and when you do their intersection, you get the null set. So that would mean that these sets are disjoint if you never have anything overlapping with them. Oops, let me make that E. That brings us to an important definition. And it says that we can have a partition of a set where we break it into subsets. And if the union of all of those subsets is the larger set or the superset, and if each one of the individual sets, when you take them pairwise, if they are mutually disjoint. This idea of a partition is something that can happen in lots of different places. If we have just some set and we slice it into different pieces, calling them A, B, C, and D, this is a partition if it meets those two properties. First of all, the first property is if you take the union of A, B, C, and D, if you get, if I call this the universe here, if I get the big set, the superset. So if the union of all the subsets gives us the superset, that's the first property. The other property is if you take A intersection B, A intersection C, A intersection D, B intersection, we've already done A, B intersection C, B intersection with D, and C intersection with D. Those are all the different things that could possibly intersect. If every one of those produces the null set, If we have these two properties, this is the one that says all of the sets, when you find their union, it gives you the big set, the superset. And the second one says that all of the subsets are non-overlapping, or we can say all the subsets are disjoint, or we can say all of them are mutually exclusive. There's lots of places where you see the word partition. You see the partition in everyday usage when you talk about taking a room, like a great big ballroom, and making dividers in the room. So you divide it into room A, B, and C. Well, any particular person or object that's in one of the rooms can't be in any of the other two rooms. And if you combine all the rooms together, you get the entire ballroom. This is also the same thing we're doing when we do a partitioning in computer science of a disk drive. When you have a physical disk drive and you break it into partitions, you are making virtual disk drives where when you put all of the disk drives, all of the virtual disk drives together, you get the physical disk drive, and nothing is in two of the virtual disk drives at the same time. Here is another example of a partition that we've worked with before. We've seen that we can take every integer and declare the integer to be even or odd. When we take the integers and we segregate them into the evens and the odds, this is partitioning them. If we combine the even integers and do a union with the odd integers, we get all of the integers. And if we do the intersection of the even integers with the odd integers, we get the null set, because there are no numbers that are both even and odd. Well, here's a related question for you. Is the set of positive integers and the set of negative integers a partition of the integers? Certainly, if you take the positive integers and do an intersection with the negative integers, you get the null set, because no integer is both odd and even. So it is fulfilling the second part of the definition of a partition. We're okay on the second part. If you take the positive integers and do a union with the negative integers, do you get all of the integers? No, because we're missing 0. So since this part is not true, we cannot partition it this way. However, the positive integers, 0, and the negative integers is a partition. Ooh, spelled partition wrong. Is a partition of the integers. We're going to use the word partition in describing a lot of different things, so you have to be able to understand when something is and is not a partition.